We have to increase the tolerance here. The vibration is too high.
It measures exactly 4.5 inches. The schematic confirms it.
I'll adjust the blueprint immediately. Give it another quarter turn. That should hold her. Tighten the fitting on cylinder 3.
To what tolerance, sir?
Firmly, but do not crack the housing.
The power output is still unacceptable, Johnson.
We're pushing the manifold pressure as high as she'll go, sir. The tolerances are too tight.
January 1940. East Hartford, Connecticut. Inside a cold factory hall, the air smells of oil, hot metal, and unfinished work. Steel presses stand silent between shifts. Drafting tables are crowded with blueprints that still do not solve the problem in front of them. Outside, snow settles on brick walls that were never meant to carry the weight of a coming war. Across the Atlantic, aircraft engines are already screaming over Europe. German bombers fly on power plants refined through years of preparation. British fighters depend on engines pushed to their limits, day after day. In the Pacific, Japan accelerates its own designs with ruthless urgency. But here in the United States, something critical is missing. America has airplanes on paper. It has pilots in training. It has factories capable of building airframes by the thousands. Yet the heart of air power, the engine, remains dangerously underdeveloped. Existing designs are fragile. Production capacity is thin. Time is slipping away quietly. In this moment, before Pearl Harbor, before public mobilization, a small group of engineers faces an unspoken truth. If they fail, American air power may never leave the ground. And that realization pulls the nation toward a single, irreversible decision. By the late 1930s, air power had become the clearest language of modern war. Europe learned this first. Germany rearmed openly after 1935, reshaping its military around speed, coordination, and striking power from the air. The Luftwaffe was not just an air force. It was an extension of German industry. Aircraft, pilots, fuel, and engines were developed together, tested together, and refined together. When German bombers crossed into Poland in September 1939, their engines were already battle-hardened machines, capable of sustained combat operations. Britain, watching from across the Channel, had drawn similar conclusions earlier. The Royal Air Force invested heavily in engine development throughout the 1930s, recognizing that range, climb rate, and reliability mattered as much as guns or armor. The Rolls-Royce Merlin was not an accident of genius. It was the result of deliberate, long-term planning that assumed another European war was inevitable. Japan followed a different path, but reached the same destination. Lacking natural resources and industrial depth, Japanese engineers pursued lightweight, high-output engines that prioritized range and agility. Their aircraft engines were optimized for long-distance operations over ocean, allowing Japan's air power to project far beyond its shores. Across the world, one truth became increasingly clear. Aircraft without reliable engines were useless, no matter how advanced the airframe appeared. The United States, however, stood apart from this trajectory. After the First World War, America had dismantled much of its wartime aviation infrastructure. The nation returned to isolation, reducing military budgets and scaling back research programs. Aircraft development continued, but slowly, fragmented between civilian experimentation and limited military contracts. The U.S. Army Air Corps existed, but lacked the authority and funding to force large-scale innovation. In the 1920s and early 1930s, American aviation focused on mail delivery, passenger travel, and record-setting flights. These pursuits advanced aerodynamics and navigation, but they did little to prepare the country for mass production of combat-ready engines. Performance goals were modest. Reliability mattered, but only in peacetime conditions. Engines were often treated as components rather than systems. Many designs were improved incrementally, not reinvented. When budgets tightened, engine programs were among the first to be delayed or canceled. By 1938, the consequences of this neglect were becoming difficult to ignore. American aircraft designers wanted more power, heavier bomb loads, higher altitudes, longer ranges. But available engines struggled to deliver. Cooling failures were common. Materials warped under sustained stress. Power outputs that looked impressive in test conditions collapsed under operational demands. The Army Air Corps knew the problem but lacked leverage. Its leadership could request improvements, but it could not dictate the pace or scale of industrial transformation. Engine manufacturers worked cautiously, aware that massive investments could evaporate with a single budget decision from Congress. Meanwhile, foreign intelligence reports grew more alarming. German engines were reaching power levels that American designs could not reliably match. British fighters were climbing faster. Japanese aircraft were flying farther than expected. Each report widened the gap between perception and reality inside the United States. Yet the public saw none of this. Newspapers spoke of neutrality. Politicians promised distance from European chaos. Factories continued operating as if time were abundant. Inside engineering offices and military planning rooms, a different understanding took shape. If war came suddenly, the United States would not lose in the air because of courage or tactics. It would lose because it lacked enough engines capable of surviving modern combat. And that realization forced American planners to confront a deeper question: whether the nation could redesign its aviation heart fast enough to matter. By 1939, the weakness of American aircraft engines was no longer theoretical. It was measurable, documented, and increasingly urgent. The U.S. Army Air Corps faced a stark imbalance between ambition and capability. New bomber concepts demanded higher altitudes and longer ranges. Fighter designers pushed for greater speed and climb performance. Yet the engines available to them remained constrained by older assumptions: short flight durations, limited stress tolerances, and peacetime maintenance cycles. Liquid-cooled engines, particularly inline designs, appeared attractive on paper. They offered slimmer profiles and aerodynamic advantages. But in practice, they introduced fragility. Radiators, coolant lines, and pumps added complexity and vulnerability. A single bullet or piece of shrapnel could drain coolant and seize an engine within minutes. European air forces accepted these risks because they had no alternative. Britain invested heavily in protecting its Merlin-powered aircraft through tactics and redundancy. Germany, confident in short-range operations over land, tolerated the trade-offs. The United States, however, faced different realities. American aircraft would need to fly vast distances, over oceans, over deserts, over terrain where emergency landings were often impossible. Reliability was not optional. It was fundamental. Radial engines offered a different path. Air-cooled radials eliminated coolant systems entirely. They were heavier and created more drag, but they were inherently robust. Cylinders could absorb damage and continue operating. Cooling was simpler. Maintenance was easier. For long-range operations and sustained sorties, radials offered endurance where elegance failed. Yet in 1939, America did not possess a modern, high-power radial engine suitable for the coming war. Existing radials were reliable but underpowered. Attempts to push them harder resulted in overheating, detonation, and mechanical failure. As power increased, tolerances tightened beyond what American manufacturing methods could consistently achieve. This was not just an engineering challenge. It was an industrial one. Precision machining at scale remained a bottleneck. Metallurgy lagged behind theoretical designs. Components that worked in prototypes failed when reproduced in volume. Each improvement demanded new tools, new processes, and new training. Time, however, was shrinking. In April 1939, President Franklin D. Roosevelt asked Congress for increased funding to expand aircraft production. The request signaled concern, but did not immediately solve the engine problem. Airframes could be built quickly. Engines could not. The Army Air Corps began pressing manufacturers harder. Contracts grew larger. Expectations sharpened. Failure would no longer be absorbed quietly. It would stall entire aircraft programs. Among American engine firms, one company stood closer to the edge of possibility than the others. Pratt Whitney, founded in 1925, had built a reputation for reliability in civil aviation. Its earlier radial engines were known for durability rather than extreme power. They had powered airliners and military transports with steady success. But what lay ahead required more than refinement. It required an engine that did not yet exist. An engine capable of producing unprecedented power while remaining air-cooled. An engine that could survive long flights, combat damage, and mass production without collapsing under its own complexity. The company's engineers understood what this meant. Incremental improvement would not suffice. Existing designs could not simply be enlarged or strengthened. The limits of materials, cooling, and combustion had already been reached. To move forward, they would have to start again, rethinking cylinder arrangement, airflow, supercharging, and manufacturing methods simultaneously. And they would have to do it with war approaching faster than any design cycle had ever allowed. The moment demanded a decision that would define American air power for the rest of the conflict. In 1940, American industry was powerful, but unprepared for precision at wartime scale. Factories were designed to build engines in limited numbers, with tolerances that allowed for adjustment and rework. That approach collapsed when power outputs climbed. At higher stresses, even microscopic imperfections became catastrophic. Bearings overheated, pistons seized, crankshafts twisted under loads they were never meant to endure. For Pratt and Whitney, the challenge was not only to design a new engine, but to reinvent how engines were built. New machine tools were required. New inspection standards had to be enforced. Entire production lines needed restructuring before a single engine could be delivered. This transformation had to occur without interrupting existing output, under the pressure of contracts that allowed no delay. Industry was no longer a backdrop to war. It was the battlefield itself. The engineering problems were relentless. Air-cooled radials depended on airflow to survive. As cylinder counts increased, cooling became uneven. Rear cylinders overheated. Power gains produced destructive vibration. Combustion pressures climbed faster than materials science could comfortably support. Engineers faced contradictions at every turn. Increased power and cooling failed. Improved cooling and drag increased. Strengthened components and weight erased performance gains. Each solution created a new problem elsewhere. Supercharging emerged as a necessity, not a luxury. Without forced induction, engines could not maintain power at altitude. But superchargers added heat, complexity, and failure points. Integrating them into an already strained design pushed tolerances to the edge of feasibility. This was engineering without safety margins. Behind every calculation stood people who understood the stakes. Designers worked extended hours, often sleeping near drafting tables. Test engineers waited beside running engines, listening for changes in pitch that signaled imminent failure. When engines exploded on test stands, no one reacted with surprise, only with quiet calculation. There was no public recognition, no speeches, no medals. Failure meant redesigning parts overnight and running the engine again the next morning. These engineers were not chasing innovation for its own sake. They were racing an invisible clock. They knew that every delay on the factory floor translated directly into vulnerability in the air. And as pressure mounted, The focus shifted from effort to decision, because someone had to choose a direction that could not be reversed. At Pratt Whitney, leadership faced a dilemma that extended beyond engineering. The company could pursue conservative improvements, safer designs that met existing requirements, or it could gamble on engines that pushed beyond proven limits. Choosing caution meant delivering engines that would be obsolete before they reached combat. Choosing ambition meant risking failure on a scale that could cripple the company and delay American Airpower entirely. Executives, in coordination with Army Air Corps officials, made a decisive choice. They authorized development paths that assumed success where no precedent existed. Funding was redirected. Teams were reorganized. Authority shifted away from incremental testing toward accelerated experimentation. This was not recklessness. It was calculated acceptance of risk, driven by the understanding that delay was the greater danger. While American engineers struggled to break new ground, German engine manufacturers operated from a position of maturity. BMW and Daimler-Benz had spent years refining high-output engines under government direction. Their factories had already absorbed the lessons of mass production. Failures had occurred earlier, when time was still available. British firms, though strained by war, benefited from continuity. The Merlin evolved through successive variants, each informed by combat experience. Improvements arrived not in theory, but under fire. The United States lacked this progression. It had to leap forward in a single bound, skipping years of operational learning and compressing them into months of testing. That disparity sharpened the urgency inside American engine plants. By mid-1940, time ceased to be an abstract concern. France fell in weeks. German aircraft dominated the skies over Western Europe. Reports arriving in Washington carried a sense of inevitability. Neutrality no longer guaranteed safety. Production schedules were rewritten repeatedly. Deadlines moved forward even as designs remained unfinished. Engine programs ran in parallel with factory construction. Blueprints were revised while tooling was already being installed. This compression of development and production violated every traditional rule of engineering management. It was the only path available. Once the direction was chosen, there could be no pause to reconsider. The engines would either succeed in time, or the nation would enter the war unready. And that gamble set the stage for a turning point where theory met steel, heat, and motion. The turning point began not with success, but with controlled failure. In early 1940, Pratt and Whitney committed fully to two engine paths that would define American airpower: the R-1830 Twin Wasp and, more ambitiously, the R-2800 Double Wasp. On paper, they promised what the Army Air Corps desperately needed: high power, air-cooled reliability, and scalability. In reality, they existed only as drawings, calculations, and fragile prototypes. The R-1830, an 18-cylinder radial, was already flying in limited numbers, but pushing it toward combat performance exposed its weaknesses. Cooling remained uneven. Supercharger integration strained bearings. At high altitude, power delivery faltered unpredictably. Every solution introduced a new vulnerability. The R-2800 represented a far greater leap. With 18 cylinders arranged in 2 rows and a displacement previously considered excessive, it aimed for power outputs that rivaled liquid-cooled engines, without the protection of coolant. No American radial had ever operated reliably at such levels. The thermal loads alone threatened to tear the engine apart. Test stands became battlefields. Engines ran for minutes, sometimes seconds, before failing. Pistons cracked. Valves warped. Bearings overheated until they welded themselves in place. Superchargers shattered under rotational stress. Each failure was documented, dissected, and fed back into redesigns that often altered multiple systems at once. Cooling proved the most unforgiving adversary. Airflow through the tightly packed cylinders resisted prediction. Wind tunnel data contradicted real-world results. Engineers reshaped fins, adjusted baffles, and reoriented ducts, chasing fractions of improvement that determined survival or destruction. Rear cylinders, starved of air, became the silent killers of otherwise promising designs. Metallurgy followed close behind. Alloys that performed well under moderate loads collapsed under sustained high power. New heat treatment processes had to be developed alongside the engines themselves. Suppliers were pushed to meet tolerances they had never been asked to achieve. The pressure intensified as Army inspectors observed testing firsthand. Acceptance standard hardened. Temporary fixes were rejected. Only repeatable performance mattered now. By mid-1940, the choice was clear. Either the engines would mature rapidly, or entire aircraft programs would stall indefinitely. And as failures mounted, the line between experimentation and production blurred, because the engines were no longer being developed for the future. They were being built for an approaching war. By late 1940, the failures began to change character. Explosions on test stands grew less frequent. Overheating still occurred, but it no longer appeared without warning. Components failed later in test cycles, after hours instead of minutes. These were not small victories, but they were measurable. The R-1830 stabilized first. Refined supercharging improved altitude performance. Cooling baffles were standardized. Manufacturing tolerances tightened enough to allow engines to perform consistently across production runs. What had once been a fragile design became dependable under sustained load. But it was the R-2800 that marked the true turning point. After months of incremental redesign, the engine reached power levels previously considered unrealistic for an air-cooled radial. More importantly, it sustained them. The double wasp no longer destroyed itself under test. It endured. Army acceptance trials followed. Engines were run continuously, pushed beyond normal operational limits, and subjected to temperature extremes. Inspectors watched for oil pressure fluctuations, vibration anomalies, and power degradation. When failures occurred, they were no longer systemic, they were isolated. Approval did not come with celebration. It arrived quietly, stamped on a paperwork that unlocked mass production. Factories that had been retooled in uncertainty now surged forward with purpose. Production lines accelerated. Workers trained under compressed schedules began assembling engines at rates that would have seemed impossible months earlier. The effect rippled outward. Aircraft designers suddenly had something solid to build around. The engines were no longer variables. They were foundations. Bombers, fighters, and transports took shape around the power plants that could finally support their demands. By the time the United States edged closer to open war, American air power was no longer an aspiration. It was becoming an industrial reality. And as these engines left factory floors and entered aircraft, their true test awaited far beyond test stands and acceptance trials. Once the engines stabilized, scale became the new battlefield. With war looming and then arriving abruptly after December 1941, the United States demanded numbers no aviation industry had ever produced. Engines were no longer measured in dozens or hundreds. They were counted in tens of thousands. Every aircraft order multiplied the strain on factories already operating at the edge of capacity. Pratt and Whitney expanded relentlessly. New plants were built. Existing facilities ran around the clock. Supply chains stretched across the continent, feeding raw materials, precision components, and subassemblies into an increasingly synchronized system. Standardization replaced customization. Interchangeable parts became mandatory rather than aspirational. The R-1830 and R-2800 moved from engineering achievements to industrial pillars. The twin WASP-powered aircraft such as the B-24 Liberator, the C-47 Skitran, and the PBUI Catalina, machines that depended on range and reliability more than elegance. These engines flew supply routes, anti-submarine patrols, and strategic bombing missions where engine failure meant isolation or death. The double WASP transformed frontline combat aircraft. It powered the P-47 Thunderbolt, an aircraft that traded sleekness for survivability and firepower. It drove the F-4U Corsair, whose raw power demanded structural redesigns just to contain it. It lifted bombers, attack aircraft, and naval fighters off short runways and carrier decks alike. Production figures escalated rapidly. By 1943, Pratt Whitney was producing thousands of engines per month. Defect rates fell even as output increased. The engineering compromises that had once threatened collapse were absorbed into stable manufacturing processes. The strategic impact was immediate. American aircraft could now operate at altitudes and ranges that matched or exceeded enemy capabilities. Losses due to mechanical failure declined. Mission planning became more aggressive, no longer constrained by engine fragility. Airpower shifted from experimental to dependable. And as these engines reached combat zones across Europe and the Pacific, their real influence began to reveal itself. Not in isolated tests, but in sustained warfare. Combat revealed what test stands never could. In Europe, Pratt Whitney powered aircraft flew in weather that erased margins. Cold thickened oil. Flak tore into cylinders. Long missions pushed engines far beyond planned service intervals. Yet the Radials endured. Crews learned to trust them, not because they were flawless, but because they kept running when conditions collapsed. The P-47 Thunderbolt became the clearest symbol of this endurance. Heavy, blunt, and seemingly overbuilt, it returned from missions riddled with damage that would have destroyed more delicate aircraft. Its R-2800 absorbed punishment, losing cylinders yet continuing to turn the propeller. Pilots credited survival not to armor alone, but to engines that refused to quit. In the Pacific, reliability became decisive. Distances were vast. Landing options were rare. Engine failure often meant water, jungle, or nothing at all. Aircraft powered by Pratt and Whitney radials operated from primitive airstrips and carrier decks alike. Salt air, heat, and humidity punished machinery relentlessly. Yet the engines proved adaptable, maintainable, and resilient under conditions few had anticipated during design. By contrast, enemy engine programs struggled to scale. German manufacturers faced material shortages and bombing that disrupted production quality. Japanese engines, optimized for lightness, deteriorated as fuel quality declined and maintenance resources disappeared. Power advantages faded. Reliability collapsed. American production, however, accelerated. By war's end, Pratt Whitney had produced well over 350,000 aircraft engines. Entire Allied air campaigns depended on them. Strategic bombing, naval aviation, transport operations, all rested on power plants born from an industrial gamble made before the United States officially entered the war. The engines did more than enable aircraft. They reshaped strategy. Commanders planned missions assuming endurance. Logistics chains expanded confidently across oceans. Air superiority shifted from fragile dominance to sustained control. And when the war ended, the factories did not vanish. The processes, skills, and industrial culture forged under pressure carried forward. Into jet development, post-war aviation, and a new understanding of what industrial preparedness truly meant. The engines had outlived the crisis that created them. Pratt and Whitney's radial engines were never glamorous. They did not appear in headlines or newsreels. They did not carry the romance of daring pilots or spectacular dogfights. Yet they carried the weight of victory itself. These engines proved that industrial courage could rival battlefield valor. Quiet engineering decisions, made under impossible constraints, determined outcomes before a single bomb fell or a fighter engaged its enemy. The difference between success and failure in the air rested on tolerances, airflow, and the endurance of steel. History remembers battles, but the radial engines remind us that wars are won long before the first shot. Reliability, production, and ingenuity created a foundation upon which strategies could succeed. They allowed American aircraft to survive when theory alone would have failed, giving pilots the chance to fight, return, and fight again. In the broader sweep, this moment reshaped warfare itself. It demonstrated that technological mastery and industrial readiness could be decisive. It underscored a timeless lesson, that preparation, precision, and persistence are as lethal as any weapon. And when the engines finally roared across skies over Europe and the Pacific, they carried more than propellers. They carried the quiet, invisible power of a nation learning to rise from its own industrial limits. They were the heartbeat of American air power. And without them, the story of World War II would have been very different.